Okay, now we're going to get into the main point of this section is we're going to compute surface areas as integrals. Okay, surface areas, they're actually going to play a really important role in the next fundamental theorem of calculus. That's why we're spending some time developing this machinery. And in the previous video, we showed that cross product, it actually corresponds to an area of a parallelogram. So, in fact, what we'll do is we'll split an arbitrary surface into a bunch of parallelograms. So then it's going to be the sum of each of these parallelograms. And that'll be an integral. So that's basically the idea. And the question, though, is how do you do it? Like in the video before that, we knew that if you did the same procedure in 1D, and you split it up using line segments, we knew that the length of that displacement vector was just the derivative, right? Well, it turns out that in 2D, we'll have something very similar, and the dt will change to a du dv. And this single derivative, it'll turn into two derivatives. And the only way we can combine two derivatives in a nice way is with a cross product. We can do a dot product and a cross product, but the dot product gives you a number, but remember that this is the length of a vector. So the dot product wouldn't work, right? So the cross product is the only other thing you can think of. So it turns out this will be our dA. And so then the formula we'll get is the area will be the double integral of this dA, which is a function of uv. So it'll be the integral of this cross product between the partial derivatives times du dv. And of course, because I am the laziest person, I'm just going to denote r sub u as the partial derivative with respect to u. So this is the area. And it'll be over whatever domain we have. And note that our uv, we're treating this as points in the surface. Recall that in the 1D case, we just denoted r of t as all points in the line, or the curve, really. So now this is the natural 2D analog. And so once we have that surface explicitly, we can compute the area using this integral. But let me just unpack why it looks like this. Because it's not really all that obvious, is it? And I think the main thing to explain is why is there a cross product and why does it actually work? So let me just unpack a couple of things. So first of all, look at the dimensions. Does this actually correspond to an area? Well, we have two r's, so that's meters times meters, and they're partial derivatives, right? So there's going to be u and a v downstairs. But notice that we're multiplying by du dv. So there'll be a u upstairs and a v upstairs. So it'll cancel, give you meters squared. Right? So heuristically what I'm doing is I'm canceling the u's and I'm canceling that v. That just shows you the dimensions are correct. This actually does correspond to an area. It's also positive, which is why we need the length. And not, for example, ru dot rv without an absolute value or something. That's just, I'm telling you why there needs to be a length there. So that explains this. So finally, and I think the most important thing is why does ru cross rv work? because you would think you could put a lot of expressions here. Like, for example, why not just the integral of du dv? Why does this not correspond to the area? Well, for one, it doesn't have dimensions of area because you need meters, not u's and v's. For example, u could be an angle, and v could be another angle if we're in spherical coordinates, so that's clearly not the right dimensions. So the question is, why does RU cross RV work? So it goes back to this idea of splitting the surface into parallelograms. And we know the area of a parallelogram. So if we have our surface, then what I will do is I will model it off the 1D case, where if we have any point, we'll increment it slightly by dt. So here's r of t, and here's r of t plus dt. And so what I'll start off with here is I'll start off with r of uv, and I will increment it slightly by, if I'm on the t-axis, what I'm doing is I'm sending t to t plus dt, and if I'm on the uv plane, I'm starting with uv, and I'm sending it first to u plus du, then I'm sending it to v plus dv, and I will get two associated points, right? So I will get something over here that will be r when we increment u, and I will get something maybe over here. Who knows what it looks like, but it'll be somewhere when we increment dv. And there will be two associated vectors with these points. And we're interested, of course, in those displacement vectors. Right? Because that gives us a parallelogram. Let's see if I can draw that parallelogram nicely. Oh, this isn't too bad. So now the area of this parallelogram, it'll be the cross product of A times B, right? Where A will be the u displacement vector, and B will be the v one. So now let's just calculate these really quickly. If you go from u to du, and then you subtract, I'm suppressing the v dependence because I'm lazy. So that'll just be the partial derivative, right? Times du. This is the mean value theorem, right? Because y of b minus y of a, it's b minus a times y prime at some point. That's really all this is saying. So you would have something similar for v, and you just need to use the partial derivative in the v direction. And then there's plus a higher order term if you want to actually Taylor expand that. But so these things follow from Taylor expansion or mean value theorem, however you like to do it. And so now we just plug it in. So dA will now be, well, it'll be the length of that, right? Because dA is a number. So it'll be RU cross RV, and if we take the du and the dv out, I will just get a du dv on the outside. That's exactly what we want. Because remember, in this expression, we have the cross product times du dv. So that's the area of a small parallelogram. And so to get a general area, what you do is you just do that a lot. So in the entire UV space, you just partition it. As usual, if we're doing double integrals, you just make a very fine grid. Each of these squares corresponds to a parallelogram on the surface. So then the total area is just the integral of the small areas, which we already computed. And so what we'll do later is we'll see how some actual explicit examples of how this can be done. Thanks for watching.